let's consider our r double prime vector. The second derivative of our position function, well, is the derivative of our first derivative, tells us at what rate the first derivative is changing. And if this is motion, if we're interpreting this function as representing motion, this is going to be our acceleration. It's very easy to calculate the derivative. We get, start out wrong here, cosine t I minus, good heavens, making terrible mistakes already. Charge myself $1 and go on. Okay, that will be minus 2 sine t j and plus 0k. There's no k component to the acceleration. The velocity in the k direction is not changing, since the velocity in the k direction is always 1/2. It's not going to change. It's not going to have it contribute anything to the rate of change. So let's compare the r double t function with the r of t function, which, if you recall, was cosine t I plus 2 sine t j plus 1/2 t k. We see that the r double prime of t component in the I direction is identical. It's not identical because this is negative. Got a negative here and a negative here. Identical, but this is positive. Okay. The I component of our second derivative function is equal and opposite to the I component of our original function. And the j component of our second derivative function turns out to be equal and opposite to the j component of our original function, which means that for this function, the rate of change in the x and y directions is always back toward the center. If we sketch a series of position vectors, of r of t vectors, then this tells us that our acceleration vectors are always back in the direction opposite the direction of our velocity. There's also a k component, so that as we rise along the helix, we're moving upward at a constant velocity, so we have no upward component of the acceleration. So the acceleration is always back toward the z-axis in the xy plane.